Welcome to a lesson with Dr. Powell. Let's look at an example of an additive function and use the fact that it's additive to verify that it's injective. So what does it mean to be injective? That means that all the fibers only have one element. Now, if a function is additive, something really nice happens. All of the fibers are simply shifts, like set addition shifts of just a single element so a single element, such like A, plus the F inverse, or the preimage, that is, the preimage of the zero element. So this function right here, let's think of it as it goes from R2 to R3. And the zero element, the additive identity of this additive group right here, is 0, 0, 0. Okay, so we look at the preimage of the zero guy, which is like 0, R3. We look at the preimage of that, it's a set. And if we add an element to it, that's actually going to be a fiber. All fibers are just additive shifts of this guy right here. So, so keeping that in mind, if you have set addition with a single element to a whole set, what happens is you just take that single element and you just add it to each thing in the set. So the set really will look the same. So in order to show that this is injective, we need to show that this guy right here only has one element in it. Then all the fibers will only have one element in it. It just suffices to look at this guy right here. Okay, so let's just look at the preimage of 0. And that's enough to show it's injective. So how do you find a preimage or a fiber of something? Well, we simply do this. X plus y is equal to 0. X minus y is equal to 0. X is equal to 0. We just want all these guys going to 0. Okay, and we notice that x has to be 0. Well, if x is 0, then that forces y to be 0. Oh my goodness, that means there's only one thing in it. That means this function is injective. It's a quick check. All we have to see is that the only way of making all zeros is for x to be 0 and y to be 0. And as soon as we know that this function is injective. Thanks for watching.